Now there's a different way to go with this that we actually also find appealing. And let me just kind of talk your way through this without really doing it. I guess I didn't really do it the other way either. But so here, we said we got this small increment by imagining continuation values that only depend on signal histories. Suppose we do the following. Imagine computing a continuation value for some plan, consumption investment plan, that actually, in this case, depended on, say, on iota. We go under the, we say, well, suppose I knew what iota was, and let's figure out the corresponding continuation value, kind of condition on that. So we do continuation values conditioned on not only that of the history of the data, but also the unknown parameter. And then, in the current period, we take that continuation value and we make a robust adjustment to it. We say, well, from that continuation value, now we look at the consequences of kind of changing the posterior over the parameter iota. Since we're not just looking at an increment now, we're looking at the entire future of this consequences of this plan. This will there's no need to do the scaling, which we talked about. The scaling by the sample horizon doesn't matter anymore. And this is the corresponding continuation value. It's got these two different sources now, misspecified dynamics and misspecified state estimation, but you don't have to engage in the scaling here because now the potency is there because you're looking at the consequences for the entire future plan of kind of changing this, changing your estimate. Now to formally do this in a rigorous way, what you have to do is you have to imagine the decision maker is playing a game against a future version of himself. They all kind of share common preference. Well, they kind of share a common objective, but they're going to be led to distorting things in potentially different ways. And so you have to limit. And so the single decision problem, strictly speaking, has to become a game a person plays with himself in order to confront changing tastes. But this is fairly standard in the decision theory literature. I guess Peleg and Yari are some initial contribution to this. The whole hyperbolic discounting literature is a similar, takes a similar approach to say what we're talking about here. So anyway, this changes the consequences of the misspecified estimation by not just looking over what happens over over an increment of time. Since you're conditioning the continuation value on the object you're trying to estimate, that increases the potency of changing the posterior distributions, or the consequences of changing them. And so this is our alternative way. And what we find to be useful here is working through how these different changes impact on likelihood functions given signal histories. And so we've got results trying to there's kind of a whole history of this. Previously, which we were looking at these type of methods for processes and for decision problems in which there was no estimation problem, and here we're extending these ideas to ones in which there's unknown parameters, unknown states, and the like. Anyway, so under our suggested scalings, there is a meaningful trade-off between sources of misspecification, these two that I sketched out over here. Whereas under scalings, the second channel just gets eliminated if you take these limits. So that's what's in the paper. Of course, I've talked about this all in the context of a pure estimation problem. What we're really interested in are these hidden state Markov chain models, under which there's a state which is moving around over time that's not directly observed, and you're trying to track that state given historical data. And these methods are extendable to that case in a direct way. But the important thing is this notion of statistical detection likelihoods give us a different vantage point on how to do this kind of calibration of concerns about ambiguity, model misspecification, or the like, and they lead us to address some things like scaling issues, which at least elsewhere in the literature we found to be a bit confusing. Did you want to say more?
So is there a way to rephrase some of this by saying the following? The scaling is induced by an entropy measure rather than that Lagrange. A scaling induced by the entropy measure would make that Lagrange multiplier theta 2 that you had an outcome and not something that you locked.
I don't know how to answer that question. So I'll let you answer it.
No, the spirit of this slide was that the statistical detection, the appeal to statistical detection, would defend that scaling by by tau.
Okay, so here. So you're asking a question. If you look at the way that you taught me how to do entropy, we always do a condition on the unknown model and then average out. The entropy that shows up in the entropy that shows up in statistical discrimination theory is all measured straight on signals, on log likelihoods of future signals given signal histories. And if we shifted to that, I don't know how to do the decision theory, but it would sharpen up this point. So the entropy measures in our paper are different. This is like, I don't know, this is like the EM algorithm or something, but because the measure that I wrote down here were log likelihoods conditioned on that iota. So I think you'd have to do something like that. And it's maybe doable. I don't know how to do it, but it's possible.
Could you say once more why the entropy is useful here?
Okay, so the thing we find appealing is the fact we're looking at log likelihood ratios. And from statistical analysis, we know that models that have similar log likelihood ratios are very challenging for a statistician to ever figure out. So we figure they'll be challenging for a decision maker. Because the decision maker kind of looks at two models that have given past histories or about the same observable implications, then how's he going to know which one to throw off the table? Okay, so that's our original motivation for it.